Hola, ¿cómo estás? Hola, buenas tardes. ¿Estás bien? Hola. Allí hacer algo, pero luego que no, es bueno, es bueno, yo voy a ver de qué es. No sé, tan así. Por hablar en los cinco. Yo te voy sí. Yeah, start. Yes, my talk. Okay. In the final part of the class, I was talking about the transconductance of the AC model or the small signal model for very, very low frequencies. Okay. I'm not including the capacitances yet, but in one of the next slides, I will present the capacitive model, which is, say, quite complicated. But we circuit designers simplify this model a lot. We use just 5 capacitors instead of 16. This is very good because the real model of the MOSFET has 16 capacitors, but only 9 of them are independent. It's like here, you see that you have 4 transconductors, but just 3 of them are independent. If you know 3 of them, you know the 4th one. Okay? So this is a simplified model for weak inversion. What's weak inversion? The current is an exponential function of the voltage. So the derivatives are very simple. Okay? So you know that the derivative of an exponential is an exponential. Okay? So we have very simple expressions. Here, the first one, GMS. GMS is just IF over 5P. But what's IF? IF is not ID. It's a part of ID, okay? But in most of the cases, we operate this device in saturation. And you know that in saturation, IF is much greater than IR. Then you can approximate IF as ID. That's it. Okay? Okay, let's go back to this figure again. You know that for saturation, this current is almost IF. Okay? And then IF is a function of VG and VS. In this example, both VG and VS is equal to 0. Because VB is also equal to 0, right? So in this picture, you have both VG, VS, and VB equal to constants, right? Okay, so you know that IF is a function of VG and VS. And as I told you before, when you have a curve like this, you can infer the value of IF from this figure, okay? So IF at this point or IF here is the same. What happens when VDS equals 0? Both IF and IR have exactly the same value. Okay. Now, okay, this is GMS. Well, what's GMD? GMD has two terms. One is similar to GMS. Okay, but when you move from the triode region to the saturation region, this is kind of a imaginary separation between these two regions. There is no clear division or clear separation between these two regions. Okay, but let's call this region here triode. The current changes a lot with VD, but here you have just a small change of the current with the drain voltage. Okay, but in case the transistor operates in this region here, the dominant term will be IR over phi t, okay? For the calculation of GMD. What's GMD? Oh, GMD is the derivative of ID with respect to VD, right? So, what's GMD? GMD is the slope of the curve. You have one GMD here, another one here, another one there. GMD is the slope of the ID versus VD characteristic. Okay. But you know that when the transistor operates in saturation, this IR becomes very, very small. Then, in most of the case, the dominant term will be sigma versus times Gm. Okay? This is a consequence of the exponential dependence of the drain current on the threshold voltage, because the threshold voltage is dependent on the DIBL factor. We have another term here, but in this case, this is 0. The SB equals 0. So this result is just a consequence of this dependence of the threshold voltage on the drain to bulk. Okay. So you have two terms. This one is the most important in the triode region. But somehow around this point here, maybe you have a combination, you need a combination of the two terms. It's, well, you should calculate or you should simulate something like that, to know what term is important, right? All right. What's GM? GM is a combination of the source and drain transconductance. So in most of the cases, you can use just this relationship here And in general, or in saturation, this coefficient is much greater than this one. But for the general case, you have this formula for calculating the transconductor. So look here. What happens when ID equals 0? ID equals 0, then GM is equal 0. Let's interpret the meaning of this. What if you change VG? What? GM is BID, BVG. Right? So what happens when you, for example, increase VG? You have another curve such as this one. But the current doesn't change if you operate the transistor with VDS equal to 0. If VDS is equal to 0, ID is equal to 0. So at the origin, at VDS equal to 0, GM is always equal to 0. And GMB is always equal to 0 as well when ID equals 0. Okay? All right. So this is the simplified model for the case of subthreshold region, right? Or the weak inversion, or when the transistor has a current which is exponentially dependent on the voltage. Okay. In saturation for any case, okay, we have these expressions here. GMD is sigma times GM. Well, GMS is a function of the inversion level, okay? And in saturation, the inversion level is equal to the normalized drain current. Because what's this ID? Just recall what is the meaning of the forward and the reverse currents. If I do this, divide by IS here, IS there, and there. This means that this is what we call the normalized drain current. IF, small IF is the normalized forward current. And small IR, the normalized reverse current. Okay? Now you can write GMS in terms of the in saturation, IF is much greater than IR. Okay? Operation here in this region means that IR is much smaller than IF. Is that clear? Oh, this approximation is also valid because what's GMS? GMS is the slope here. But this is not GMD. Okay. But look here, at the origin, what happened? The transistor is symmetrical. Then just here. Okay. What's the meaning? It doesn't matter if you change the source or the drain. The variation of the current will be the same if you change source or if you change drain by the same amount. The difference is that if you increase the source, the current decreases, and if you increase the drain, you know the current, the conventional current is from drain to source. But if the source increases with respect to the drain, the current reduces or changes sign. Okay? We have a lot of these equations in a lot of designs. They are very useful because you can see that, oh, you have a dependence here on the inversion level. You have here 2 degrees of freedom. One is the IS. You know that IS is, this is a technology parameter, N times W over L. This is a design parameter. Designers, they can choose the channel width, the channel length. Okay, and the other parameter is this one here. What's ID? ID is the drain current over IS. Okay, so you have 2 design parameters, IS and ID. Okay. I showed yesterday at the very beginning, or Wednesday, I don't remember again, but there was an example of an amplifier, and I showed that now you can exchange here silicon area for current, for power. Okay, some curves here, nothing new. Okay, they gave transconductance. In this region here, is the weak inversion region, you have a behavior which is linear in a log length scale, exactly as in the case of the current. Okay. For higher voltage, you have modification. Of course, you have a different model. You have the square law model, and the curve changes according to this picture. Okay. Okay, this picture is represents the gate transconductor for several values of Vs. Okay, and this axis is the gate voltage. The circuit that was used measure this characteristic, this one here. You change Vg. There is a switch in Vg. In this case, the drains connect to the power supply. Okay. Okay. This is another curve, which is the GM over ID, or if you want, GMS over IF. Okay. And the theoretical curve is this one here. A solid line in this picture. These symbols here represent measurements. Okay. This is for a transistor in saturation. Okay. And for 2 technologies, both for this technology, this is not a very old technology because the oxide thickness is 28 nanometers. The minimum channel length for this technology is around, I would say, 1 micrometer. This is a node technology. But we choose 25 micrometers of channel length. And the second technology is the oxide thickness is 5.5 nanometers. And in this case, the technology, I suppose, is 180 nanometers. There is a rule that we apply. The channel length, the minimum channel length is around 40 times the oxide thickness. This is a rule of thumb, approximate. Okay, it's not exact, but it's an approximation for the calculation of the minimum channel length. All right. So this these symbols, well, follow the theoretical curve very well. We measured these devices, I don't know, 30 years ago, almost. I don't remember exactly, but around 30 years ago. Of course, we have to do this for current technologies. I don't know if the symbols or the experiment will fit the theoretical curve so good as it fit. May I go on? This is a summary of the model. Okay. This is just a summary of what we have. One of the parameters is the specific current. Okay. The other one is here inside the pinch-off voltage. You have VT. Okay. You have also N here, or N. So IS, VT, and N are the basic parameters for the long channel device. Okay. Then we add two more. One of them is here, is associated with this parameter here, sigma. And the final one is the velocity saturation. It's not included in the formulas here. Okay. Let's forget about the velocity saturation. Let's say that it's not important here for our course, but it's really important for the model, the transistor model. Okay, because the transistor model should include all the regions and also the high velocity region. Okay, this sometimes you use approach for the drain transistor similar of what we use for bipolar transistor. Oh, let's extend this. Assume straight line here. You don't have. You seldom have a straight line here, but let's assume that's a straight line. Okay, you extend this line down to a voltage which we can call early voltage. Right. And this is just a mathematical method, so it doesn't have a real meaning. It's not associated with the physics. In the case of the bipolar, you sometimes calculate this early voltage in terms of phase rate modulation, because this is associated in the case of bipolar with a phenomenon which is called phase rate modulation or early effects. This is important about the gate transconductance. When the gate voltage is very, very high, you have a saturation of the value of GM, because this factor here, which is the saturation velocity. At a certain point, if you increase the drain current and increase through the increasing of the gate voltage, you will not get an advantage in terms of the transconductance, because this value will saturate at a certain value, which is given by this expression, which depends on the oxide capacitance and on the saturation velocity. Okay? So the way to increase here the transconductance at high currents, high voltage, is to increase this guy. But when you increase this W, you also increase what we call capacitance. And you don't get any benefit in terms of frequency, because the frequency is, you know, here, frequency is related to a transconductance over a capacitance. If you increase this and this by the same amount, the transition frequency doesn't increase. Okay? But this is just first order analysis. Okay. Oh, wow. Wow. Sorry. Okay. Let's talk about capacitors now. Okay. There was a big problem with capacitors in the 1970s, 1980s, and finally, some professors and students find out the solution to the problem. The problem was as follows. Transistor has a channel, this slide here. And now assume that you are not in very low frequencies. And then you have a changing sign here, and another changing signal here, another signal here. And they, well, you have signals up and down. So, hold on. What happens here? Just remember, let's assume that the source is at a constant voltage, but the drain is changing. Well, when the voltage here changes, somehow you change the invergent charge density in the channel. Oh. Where does this charge come from? From the source or from the drain? How do you know? Oh, maybe 1/2 from each side. I don't know. Okay, that was the problem when they started to model the transistor. How to model the capacitance. This one is easy. This is not a problem. This is also not a problem. But the problem is that you have a communication between this terminal and this one. They both are connected to the channel, the electron channel. So the problem was unsolved until the end of the 1980s. What was the situation before these professors and students found out what should be the model? Oh, the problem, they just model like this. Oh, let's put 1/2 to the source and 1/2 to the drain. Assume that, oh, the charge changed 1 coulomb along the channel. Oh, let's put 1/2 for the source. Oh, if the transistor is in saturation, let's put, well, 2/3 of the charge variation to the source and 1/3 to the drain. Okay, but the problem is that this model didn't conserve charge. You see, when you put something around this device, you need charge conservation. All the charge entering the device, the sum of this charge should be 0. You need charge conservation. Oh, if the channel changes its charge, it's because it comes from somewhere else. Okay, so the charge was not converged. Then this Professor Dutton in Stanford, and I suppose 1 or 2 students found out how to model this partition of charge between source and drain. Okay, okay, this is the picture of the transistor seen from the top. This is the gate charge, and they modeled, okay, they modeled the capacitance, and they discovered how to model this phenomenon, how the charge is injected into the channel, how much comes from the source, how much comes from the drain. Okay, this was the big problem. Let's assume that this is our transistor, drain, the source. There's one current that we have analyzed so far. this red line, this current is same as this one. Now, if the charge in the channel change, is because something happened. Something has changed also in the source and drain terminals. So I'm here represented how much charge is coming from the drain, how much is coming from the source. Okay. All right. This was the the problem in the old models of the transistor capacitance. Well, they solved the problem simply through these two equations. Well, the source, the charge associated to the source is given by this expression. And the source associated, charge associated with the drain is given by this expression. You see that if you add the two charges, you have the total charge in the channel. Okay, there is a problem of notation here because the Qi is charge density. Okay, and this is charge coulombs. This, okay, this here is charge density, this here is charge. Okay, if you add these two terms, QS plus QT, that integral. Okay, so what's this? The integral from source to drain of Qi dy. This is the whole charge associated, maybe a W is missing here. It's the whole charge associated with the transistor channel. This W. What's Qi? Qi is charge density. If you multiply by W, L you have. Okay, this is one. This would be for the uniform charge density. That's. Oh, this integral is the charge in the chain. Okay. Okay, let's go to an application now. So now let's define the mosfet. Then you have four terminals, right? Then you have this one here, the QG. How does the gate charge changes? Oh, this variation here depends on variation of the gate voltage, the source voltage, drain voltage. So we have this line here. Okay, the QG dt is CGG dt minus CGS. Oh, what CGS? What CGG? CGG is just the gate charge in terms of the gate voltage, right? The second one, CGS, it's minus DQD. This is similar to the semiconductor. But you see that there is a sign here. Okay, it's like in a simple capacitor. Let's go back to the simple capacitor. Can write CAB like this. CAB is E Q. Let's call this QA and this is called QB. Okay, but this charge here is the image of this one here. So instead of writing CAB as dKA dVAB, I can write it like this. CAB is minus dQB dVAB. Because this charge here is the image of this one. Of course, with a different sign. Okay? So that's the reason why you have a minus sign here and here and there. So you have a total of 16 capacitors. Wow, this is a big problem. How to include all these capacitors to solve problem, say to solve the frequency response of an amplifier or a current mirror or any device. Okay. Now, in fact, you have just 19 independent capacitors. For example, in this line here, you have one capacitance which depends on the three others. It's exactly the same case of the transconductor. Okay. In fact, you have dependence in the lines and in the columns. So finally, we can choose 9 independent capacitors. Okay. And the result, but which ones do I choose? Because I have degrees of freedom to choose the capacity. Okay. Well, finally, we'll find some capacitors which are convenient for the user and which are simple to determine. Okay. Oh, this is a lot of calculation. This is just, in fact, it's not calculation, just the explanation of why some capacitors are dependent on the other. Okay. So finally, we find that, well, these are my chosen independent capacitors. We got 3, 6, 7, 8, 9. These are the ones that I love these capacitors, so I chose them. Okay, but in fact, you don't need all of these capacitors. You need, for the usual problems, you need only 5. So the model can be reduced, I would say, first to 1, 2, 3, 4, 5. These are usual capacitors. But you have also capacitors here in this current controlled, voltage controlled current source. You see that this capacitance depends on the derivative of the drain voltage with respect to the volt. Another one here, CM, another one. So you have 2, 3, 5, 6, 7, 8. Well, in fact, you need 9, but we know that this capacitance and the both gates, the symmetric, the other capacitance, these two nodes is similar to this one. So we eliminated the 9th capacitance. So just 8 remain. But in most of the cases, what's this here? CSD, DVD, DP. You remember that. Let's take one of those terms, plus C, DV, let's say DVG, DT. I can write in the frequency domain this expression, Gm plus J omega C VG, right? This is the expression in the frequency domain. And you see that if Gm is much higher than omega C, then you can just remove this term. Okay? That's the reason why we generally don't use all the capacitors that are needed in a complete model. Okay? it's for frequency reasons, because we usually don't solve frequencies. We don't solve this problem for very high frequency, okay? Then, after removing this, what we call transcapacitance, we finally find the model, the AC model that is appropriate for solving almost all the AC problems or problems associated with what we call small signal device or small signal analysis. Okay. Okay, this seems to be quite complicated, right? You have 3 transconductors and 5 capacitors. It's still a very complicated problem. But in most of the cases, you don't need all these parameters. Let's see this example here. Let's assume that you have this problem here. An amplifier, instead of, let's put a resistance here. This is the drain. Let's put some input here, a bias and a small signal. Okay. And you see that in this case, Vs equals Vb equals to 0. Then you have this terminal connected to this one here. Okay. Then you remove this guy here. It doesn't have any effect on the circuit. Okay. Okay. What else? This current source here disappears because VSB is equal to 0. So you have a simpler problem to solve. Okay. What else? See, let's see. Between gate and source, that's fine. Oh, the other parameters should appear in this problem. Okay. But this capacitance is eliminated. The others, I don't know. Maybe one of them can be very small. Okay, so you have to make the DC analysis before the AC analysis, of course. You should know the operating point of the circuit in order to calculate all these parameters. Okay. This is a big issue. First of all, you have to solve the DC equations of your device, or to put this device in a simulator and find out what is the DC operating point. This is an example on how to apply the. This is a fictitious circuit, not a real circuit. Okay, but it's useful for explaining how is the frequency response of the MOSFET. Under this condition, this is a current source, but this is an AC current source. It's not a DC current source, okay? You have a short circuit between drain and source, and assume that you have an ammeter here, which measures the current, okay? Of course, you cannot configure this circuit like this. Something different to do this. For example, you need bias here. This is a, say, ED. So you need a meter here, measure the current. And how to insert that AC current? First of all, you need some bias of the gate voltage. After that, you need some way to inject an AC current into this device. This is not quite this because the input of this device is capacity. Okay, but you can devise a method to generate a current which, instead of coming here, comes to this capacitor. But of course, you need frequency here. Otherwise, all the current will flow through the resistance. So let's say this would be acceptable for frequency, high frequencies, or for frequencies in which this impedance is much lower than this one. Okay, so you need something here. Let's say, let's put here a source, IG, but the frequency should be such that the current that flows through this resistor is almost negligible as compared to this one. So let's assume that we have a perfect circuit limitation, okay? But this would be the way to measure the frequency response of the MOSFET. Okay? What about the model? Oh, model would become so simple. I removed here the components which are not used in this configuration because VSB is 0, right? VDD is also 0 for AC. This capacitor, oh, gate to drain. What? Oh, this is connected to ground. Okay. CBD. Bulk to drain. Oh, drain is connected to ground. The bulk is connected to ground as well. So you have a lot of components which are useless in this configuration. So if you analyze this circuit, you have a response such as this one. Okay, approximately. In fact, we should take into account that CGD, which because CGD is in parallel with these two guys. Okay, not in parallel because it has an effect here. There is this current zone. But for the input impedance, it's in parallel with this. And it provides the current, part of the current here comes through this CGD. You have some way for the current to flow, right? This IG is divided here. Part of it comes to this capacitor, and part comes to this one. Okay. For practical purposes, let's assume that in saturation, this CGD is negligible. This is not true, but the analysis doesn't change too much. Then you have what we call the unit gain frequency. In fact, the frequency response of this circuit is something like this. ID over IG. You have a gain, a current gain, ID over IG, which drops at 20 dB per decade. Oh? And what's that FT? FT is what we call the transition frequency. This is the frequency at which the gain falls to 0 dB. What's the meaning of this? If the transistor operating in a frequency below this one, you have a current gain. If the frequency is higher than this one, you have a current attenuation. Okay? So this is a kind of frequency which defines the usefulness of the MOSFET. MOSFET can amplify a current up to a frequency equal to ft. It's like in
tempo estimado no engarrafamento, 31 minutos. Siga. Não foi. Não foi escutando.